Welcome to The Explainer. Today we're diving into something that is quite literally mind-bending, the intersection of quantum mechanics and existential reality. We're unpacking decoherence and the persistence of quantum branches. Essentially, we're going to take the incredibly complex, highly abstract mathematics of quantum foundations and see what it actually says about our existence, our persistence, and the very fabric of reality itself. We are going to explore how a universe built entirely on probabilities might just hold some surprising and honestly, perhaps unsettling answers about what happens to us when the universe splits.
So, are you quantumly immortal? I know, it sounds straight out of a sci-fi movie, right? But in the Everett interpretation of quantum mechanics, which you probably know better as the many worlds interpretation, every single quantum event splits reality into distinct, parallel branches. The really unsettling quantum immortality worry suggests that no matter how incredibly unlikely your survival might be in a deadly quantum event, there's always at least one tiny, obscure branch of reality where a version of you lives on, forever. The idea is that your conscious experience would just continuously follow the branches where you survive. But does the actual cold, hard math support this terrifying kind of immortality?
All right, let's jump straight into Section 1, the quantum immortality problem. Which brings us to the mechanics in Section 2, defining a quantum branch. Okay, to really grasp what's happening here, we need to look under the hood at how these branches actually form. In the Everett interpretation, branches aren't just handed to us perfectly formed out of nowhere. They rely on this crucial concept called core screening. This process determines the approximate emergent structure of our quasi-classical branches. Think of it kind of like stepping back from a massive pointillist painting. Up close, it's just a chaotic, unpredictable mess of quantum dots, right? There is no clear picture. But core screening allows a structured, recognizable quasi-classical reality to emerge from all that underlying quantum fuzziness. It is literally the mathematical bridge between quantum chaos and the stable world we actually experience every day.
So the absolute crucial point here is this. A branch is only well-defined if it's sufficiently decohered and possesses stable redundant records. Meaning, just because a quantum event happens, it doesn't mean a fully independent quasi-classical world instantly pops into existence. The branching is always approximate. It takes sufficient decoherence, which is basically a process where the quantum system constantly interacts with its surrounding environment to lock in those stable redundant records. The environment is essentially taking measurements, over and over again. Without that stability, you don't get a separate world. You just get noise fading into the background.
And this brings us to the actual mathematical threshold for reality. What sets the practical limit below which a branch is no longer considered well-defined? Well, it happens when its Born weight is much greater than epsilon squared. Let's break that equation down for a second because it's really at the heart of the whole shebang. The Born weight essentially represents the probability, or you can think of it as the thickness of that particular branch of reality. And that symbol epsilon measures the tiny residual coherence left over in the system. So for a branch to be real, for it to actually be considered a separate quasi-classical world, its Born weight has to be significantly larger than the square of that tiny residual coherence. If a branch's weight drops below that mathematical line, it just ceases to be a well-defined world.
Let's look at the clash of theories in Section 3, mangled worlds versus decoherence.
So what actually happens to those tiny branches that fall below our mathematical threshold? We've got two sharply contrasting views here. On one side, we have the mangled worlds hypothesis, which was proposed by physicist Robin Hanson. On the other, we have the standard decoherence or coarse graining view. Now, Hanson's idea is pretty dramatic. He argues that because decoherence is never perfectly complete, those incredibly small Born weight branches don't just quietly exist in the background. Instead, they are physically mangled or entirely overwhelmed by the larger, heavier branches. The decoherence view, however, makes a much weaker, more conservative claim about what happens at the very bottom of the quantum barrel. Let's put these two side by side to see how they play out. Under Hanson's mangled worlds mechanism, small branches are completely overwhelmed by larger ones. The outcome for any observers unlucky enough to be in those tiny branches, they are effectively destroyed, where their memories are just entirely overwritten by the larger one. And the result for our big existential question? It completely solves the quantum immortality problem. If tiny branches are physically destroyed, you can't survive in them indefinitely, right? But then, look at the decoherence view. It simply says branching is approximate. It doesn't claim that low-weight branches are physically mangled or violently torn apart. It just states that below a certain mathematical threshold, they aren't considered separate quasi-classical worlds. But what about the observers inside the ones that do make the cut? Well, as we're about to see, this leaves the quantum immortality worry entirely unresolved. Moving on to Section 4, Surviving the Threshold. Well, I've got some bad news for anyone hoping the mangled worlds theory was going to step in and save them from quantum immortality. In the standard decoherence view, that cutoff threshold for branch definition, where the Born weight must be greater than epsilon squared, is extraordinarily low. I mean, it is practically microscopic. And because that threshold is so incredibly low, the branch is relevant to quantum immortality. Those tiny slivers of reality where you miraculously survive against all odds, they are still far, far above the cutoff. Those survival branches remain sharply defined, fully intact worlds. Therefore, the approximate nature of decoherence absolutely does not resolve the quantum immortality worry. The cold math essentially says those tiny worlds where you live forever are still perfectly well defined.
Which brings us to our final takeaway in Section 5, the primitivist reality.
We've traced the mechanics, we've looked at the thresholds, and we've realized that the math doesn't easily save us from the strange implications of the Everett interpretation. So, how do physicists and philosophers actually reconcile all of this? Well, this brilliantly illustrates where a lot of current thinking has landed. Everett plus Born rule primitivism is among the cleanest no-collapse pictures available. Now, a no-collapse picture just means an interpretation of quantum mechanics where the wave function never randomly collapses into a single outcome, just like the many worlds theory. Because the math of decoherence is so incredibly stubborn, and because things like the mangled worlds theory require these extra complicated assumptions that are really hard to prove, many thinkers are turning to primitivism just to keep the science clean.
So, what exactly does this primitivism entail for us? First off, it accepts the quantum formalism largely as it stands. There are no extra hidden variables, no violent mangling of macroscopic worlds just to try and save us from uncomfortable philosophical corners. Second, and honestly most importantly, it simply claims that the Born rule, the rule giving us our branch weights and probabilities, is just a fundamental law of nature. It doesn't attempt to derive the Born rule from something else. It just accepts it as a primitive, foundational fact of the universe. So while it might not cure our existential dread about quantum immortality, it is a highly coherent and increasingly discussed position in the Foundation's literature today, mostly precisely because of its sheer mathematical elegance.
I want to leave you with this final thought today. We've seen that the math dictates a universe of endless, sharply defined branches, leaving the unsettling possibility of quantum immortality wide open. And the cleanest answer modern physics has right now is simply to accept these strange probabilistic rules as fundamental, primitive laws of nature. But you really have to ask yourself, is this cold, strictly mathematical reality a satisfying endpoint to our search for meaning? Or is accepting the math exactly as it stands just the beginning of a much deeper, far stranger mystery? Think about that the next time you flip a coin.